Chemical reactions are the processes in which new substances with new properties are formed. Chemical reactions involve chemical changes. During chemical reactions, a rearrangement of atoms takes place between the reacting substances to form new substances having entirely different properties. Chemical reactions involve breaking of old chemical bonds which exist between the atoms of reacting substances, and then making of new chemical bonds between the rearranged atoms of new substances. During a chemical reaction, atoms of one element do not change into those of another element. Only a rearrangement of atoms takes place in a chemical reaction. We will now discuss reactants and products of a chemical reaction. The substances which take part in a chemical reaction are called reactants. The new substances produced as a result of chemical reaction are called products. In a chemical reaction, reactants are transformed into products. The products thus formed have properties which are entirely different from those of the reactants. Let us study the chemical reaction of magnesium with the oxygen of air now. When a magnesium ribbon is heated, it burns in air with a dazzling white flame to form a white powder called magnesium oxide. Actually, on heating, magnesium combines with oxygen present in air to form magnesium oxide. The burning of magnesium in air to form magnesium oxide is an example of a chemical reaction. In this chemical reaction there are two reactants, magnesium and oxygen, but only one product, magnesium oxide. The properties of the product magnesium oxide are entirely different from those of the reactants magnesium and oxygen. The magnesium ribbon which we use usually has a coating of magnesium oxide on its surface which is formed by the slow action of oxygen of air on it. So, before burning in air, the magnesium ribbon is cleaned by rubbing with a sandpaper. This is done to remove the protective layer of magnesium oxide from the surface of magnesium ribbon so that it may readily combine with the oxygen of air. On heating, we can perform the chemical reaction involved in the burning of magnesium ribbon as follows. Take about 2 cm long magnesium ribbon and clean it by rubbing its surface with sandpaper. Hold the magnesium ribbon with a pair of tongs at one end, and heat its other end over a burner. The magnesium ribbon starts burning with a dazzling white flame. Hold the burning magnesium ribbon over a watch glass so that the magnesium oxide powder being formed collects in the watch glass. Characteristics of chemical reactions. In a chemical reaction, the substances known as reactants are converted into new substances called products. The conversion of reactants into products in a chemical reaction is often accompanied by some features which can be observed easily. The easily observable features, or changes, which take place as a result of chemical reactions are known as characteristics of chemical reactions. The important characteristics of chemical reactions are: 1. Evolution of a gas. 2. Formation of a precipitate. 3. Change in color. 4. Change in temperature. 5. Change in state. The method of representing a chemical reaction with the help of symbols and formulae of the substances involved in it is known as a chemical equation. Let us take one example to understand the meaning of a chemical equation clearly. Zinc metal reacts with dilute sulfuric acid to form zinc sulfate and hydrogen gas. This reaction can be written in words as zinc plus sulfuric acid give rise to zinc sulfate plus hydrogen. This is known as the word equation. We can change this word equation into a chemical equation by writing the symbols and formulae of the various substances in place of their names. Now, symbol of zinc is Zn. Formula of sulfuric acid is H2SO4. Formula of zinc sulfate is ZnSO4. And formula of hydrogen is H2SO. Putting the symbols and formulae of all the substances in the above word equation, we get the following chemical equation. The substances which combine or react are known as reactants. Zinc and sulfuric acid are the reactants here. The reactants are always written on the left-hand side in an equation with a plus sign between them. The new substances produced in a reaction are known as products. Zinc sulfate and hydrogen are the products in this case. The products are always written on the right-hand side in an equation with a plus sign between them. The arrow sign pointing towards the right-hand side is put between the reactants and products. This arrow indicates that the substances written on the left-hand side are combining to give the substances written on the right-hand side in the equation. It should be clear by now that a chemical equation is a shorthand method of representing a chemical reaction. Balanced chemical equations. A balanced chemical equation has an equal number of atoms of different elements in the reactants and products. In other words, a balanced equation has an equal number of atoms of the different elements on both the sides. This point will become more clear from the following example. Zinc reacts with dilute sulfuric acid to give zinc sulfate and hydrogen. This can be written in equation form as Zn plus H2SO4 give rise to ZnSO4 plus H2. Let us count the number of atoms of all the elements in the reactants and products separately. Number of Zn atoms in reactants 1. In products 1. Number of hydrogen atoms in reactants 2. In products 2. Number of sulfur atoms in reactants 1. In products 1. Number of oxygen atoms in reactants 4. In products 4. We find that the reactants contain one zinc atom and products also contain one zinc atom. Reactants contain 2 hydrogen atoms and products also contain 2 hydrogen atoms. Similarly, reactants contain 1 sulfur atom and products also contain 1 sulfur atom. And finally, reactants contain 4 oxygen atoms and the products also contain 4 oxygen atoms. Thus, there is an equal number of atoms of different elements in the reactants and products, so the above chemical equation is a balanced equation. Since the number of atoms of various elements in reactants and products is equal, we can say that a balanced chemical equation has equal masses of various elements in reactants and products. Balancing of chemical equations. The process of making the number of different types of atoms equal on both the sides of an equation is called balancing of equation. Hydrogen burns in oxygen to form water. This reaction can be written in an equation form as H2 plus O2 give rise to H2O. In this reaction H2 and O2 are reactants whereas H2O is the product. Let us count the number of hydrogen atoms and oxygen atoms in reactants and product. The number of hydrogen atoms is equal on both the sides, 2 each, but the number of oxygen atoms is unequal. There are 2 oxygen atoms on the left side but only 1 oxygen atom on the right side. To have 2 oxygen atoms on the right side, we multiply H2O by 2 and write 2H2O, so that H2 plus O2 give rise to 2H2O. Though the number of oxygen atoms has become equal, 2 on both sides, but the number of hydrogen atoms has now become unequal. There are 2 hydrogen atoms on the left side but 4 hydrogen atoms on the right side. To have 4 hydrogen atoms on the left side, we multiply H2 by 2 and write 2H2, so that 2H2 plus O2 give rise to 2H2O. Let us count the number of various atoms on both the sides once again. Number of hydrogen atoms in reactants 4, in product 4. Number of oxygen atoms in reactant 2 in product 2. This chemical equation contains an equal number of atoms of hydrogen and oxygen on both the sides, so this is a balanced equation. Types of chemical reactions. Some of the important types of chemical reactions are 1. Combination reactions, 2. Decomposition reactions, 3. Displacement reactions, 4. Double displacement reactions, and 5. Oxidation and reduction reactions. Combination reactions. Those reactions in which two or more substances combine to form a single substance are called combination reactions. In a combination reaction, two or more elements can combine to form a compound, two or more compounds can combine to form a new compound, or an element and a compound can combine to form a new compound. Calcium oxide, lime or quicklime, reacts vigorously with water to form calcium hydroxide, slaked lime, CaO plus H2O on combination give rise to CaO2. This is a combination reaction in which two compounds, calcium oxide and water, combine to form a single compound, calcium hydroxide. A large amount of heat is released when calcium oxide reacts with water to form calcium hydroxide, or slaked lime. The substance which we use for whitewashing our house is lime, or quicklime, which is calcium oxide, CaO. We put calcium oxide in a drum and add water to it slowly. Calcium oxide reacts with water vigorously to form a white solid called calcium hydroxide, or slaked lime. With the evolution of heat, more water is then added to get calcium hydroxide solution. This calcium hydroxide solution is then applied to the walls of the house with a brush. The calcium hydroxide solution, when applied to the walls, reacts slowly with the carbon dioxide gas present in air to form a thin, shining layer of calcium carbonate on the walls of the house. Carbon, coal, burns in air to form carbon dioxide, C plus O2 on combination give rise to CO2. In this reaction, two elements, carbon and oxygen, are combining together to form a single compound, carbon dioxide. So, this is a combination reaction. Please note that when carbon, in the form of coal, burns in air, then the carbon combines only with the oxygen present in air to form carbon dioxide gas. Thus, the burning of coal in air is an example of a combination reaction. Those reactions in which heat is evolved are known as exothermic reactions. Reactions in which heat is released along with the formation of products are called exothermic chemical reactions. Example: natural gas is mainly methane, CH4. When natural gas burns in the oxygen of air, it forms carbon dioxide and water vapor. A large amount of heat energy is also produced. This can be written as CH4 plus 2O2 give rise to CO2 plus 2H2O plus heat energy. During digestion, food is broken down into simpler substances. For example, rice, potatoes and bread contain carbohydrates. These carbohydrates are broken down to form glucose. This glucose combines with oxygen in the cells of our body and provides energy. The special name of this reaction is respiration. During respiration, glucose combines with oxygen in the cells of our body to form carbon dioxide and water along with the production of energy, C6H12O6 plus 6O2, G, give rise to 6CO2 plus 6H2O plus energy. Those reactions in which a compound splits up into two or more simpler substances are known as decomposition reactions. The decomposition reactions are carried out by applying heat, light or electricity. Heat, light or electricity provide energy which breaks a compound into two or more simpler compounds. Please note that a decomposition reaction is just the opposite of a combination reaction. Example: when ferrous sulfate is heated strongly, it decomposes to form ferric oxide, sulfur dioxide and sulfur trioxide. In this reaction, the green color of ferrous sulfate changes to brown due to the formation of ferric oxide. A smell of burning sulfur is obtained due to the formation of sulfur dioxide gas. In this reaction, one substance is splitting up into three substances, so this is a decomposition reaction. It is actually a thermal decomposition reaction. They contain 7 molecules of water of crystallization. These crystals are green in color. When the green-colored ferrous sulfate heptahydrate crystal are heated, they first lose 7 molecules of water of crystallization to form anhydrous ferrous sulfate, which is white in color. And then this anhydrous ferrous sulfate decomposes to give ferric oxide, sulfur dioxide and sulfur trioxide. When calcium carbonate is heated, it decomposes to give calcium oxide and carbon dioxide. In this reaction, one substance, calcium carbonate, is breaking up into two simpler substances, calcium oxide and carbon dioxide, so this is a decomposition reaction. Please note that calcium carbonate is also called limestone, and calcium oxide formed from it is called lime or quicklime. The decomposition of calcium carbonate, limestone, on heating is an important reaction used in various industries. This is because calcium oxide, lime, obtained by the decomposition of calcium carbonate has many uses in industry. For example, calcium oxide, or lime, is used on a large scale in the manufacture of cement and glass. When a decomposition reaction is carried out by heating, it is called thermal decomposition. Thermal means relating to heat. The decomposition of calcium carbonate into calcium oxide and carbon dioxide is an example of thermal decomposition, because it is carried out by heating. When lead nitrate is heated strongly, it breaks down to form simpler substances like lead monoxide, nitrogen dioxide and oxygen. In this decomposition reaction, the colorless compound lead nitrate forms a yellow compound, lead monoxide, and brown fumes of nitrogen dioxide gas are evolved. Here, one compound, lead nitrate, is breaking down to form three compounds, lead monoxide, nitrogen dioxide and oxygen, so it is a decomposition reaction. Since the decomposition of lead nitrate is brought about by heat, therefore, it is actually an example of thermal decomposition. We can carry out the decomposition reaction of lead nitrate in the laboratory as follows. Take about 2 grams of lead nitrate powder in a boiling tube. Lead nitrate is a colorless compound. Hold the boiling tube in a test tube holder and heat it over a burner. Brown fumes of nitrogen dioxide gas are evolved which fill the boiling tube. If a glowing splinter is held over the mouth of the boiling tube, it catches fire and starts burning again. This shows that oxygen gas is also evolved during this reaction. A yellow solid is left behind in the boiling tube. Electrolysis of water. When electric current is passed through acidified water, it decomposes to give hydrogen gas and oxygen gas. In this decomposition reaction, a single compound, water, splits up to form two simpler substances, hydrogen and oxygen. This decomposition reaction takes place by the action of electricity. It is called electrolysis of water. Take a wide-mouthed glass bottle B, with bottom removed. Fix it on a stand in the inverted position. A rubber cork having 2 holes is fitted in the neck of the bottle. 2 carbon rods, called carbon electrodes, are fixed in the 2 holes of the cork tightly. The carbon rods are actually graphite rods. Fill the glass bottle 2/3 with water. Add a few drops of dilute sulfuric acid to water, to make water a good conductor of electricity. Two similar test tubes filled with water are carefully inverted over the two carbon electrodes by keeping thumb over their mouth so that initially they remain completely filled with water. Connect the outer ends of carbon rods to the two terminals of a 6-volt battery by wires having a switch in them. Connected to the negative terminal of the battery is called cathode, negative electrode. The right side carbon rod connected to the positive terminal of the battery is called anode, positive electrode. Pass in electric current through water by turning on the switch and leave the apparatus undisturbed for some time. We will see the bubbles of gases being formed at both the carbon electrodes inside the test tubes containing water. These gases are formed by the decomposition of water on passing electricity. The gases formed at the two electrodes go on collecting in the top parts of the inverted test tubes, and the water level in these test tubes falls gradually. The volume of gases collected in the two test tubes is not the same. The volume of gas collected on the negative electrode, left electrode, is double the volume of gas collected on the positive electrode, right electrode. Keep on passing electric current till both the test tubes are completely filled with respective gases. Then remove the gas-filled test tubes carefully and test them one by bringing a burning candle close to the mouth of each test tube. When a burning candle is brought near the mouth of left test tube, the gas in it burns rapidly, making a popping sound or little explosion. We know that hydrogen gas burns with a popping sound. So, the gas collected in the left test tube over negative electrode, which had double volume or two volumes, is hydrogen. When the burning candle is taken near the mouth of the right side test tube, the candle starts burning brightly. We know that oxygen gas makes things burn brightly. So, the gas collected in the right side test tube over positive electrode, which had one volume, is oxygen. Since the electrolysis of water produces two volumes of hydrogen gas and one volume of oxygen gas, we conclude that the ratio of hydrogen and oxygen elements in water is 2:1 by volume. Displacement reactions, those reactions in which one element takes the place of another element in a compound, are known as displacement reactions. Example: when a piece of iron metal, say, an iron nail, is placed in copper sulfate solution, then iron sulfate solution and copper metal are formed. CoSO4 plus Fe give rise to FeSO4 plus Co. In this reaction, iron displaces copper from copper sulfate solution. The deep blue color of copper sulfate solution fades due to the formation of light green solution of iron sulfate. A red-brown coating, or layer, of copper metal is formed on the surface of iron metal. We can perform the displacement reaction between iron and copper sulfate solution as follows. Take about 10 ml of copper sulfate solution in a test tube. It is deep blue in color. Take a big iron nail and clean its surface by rubbing with a sandpaper. Put the cleaned iron nail in the test tube containing copper sulfate solution. Allow the iron nail to remain in copper sulfate solution for about half an hour. After half an hour, take out the iron nail from copper sulfate solution. We will find that the iron nail is covered with a red-brown layer of copper metal. If we look at the test tube, we find that the original deep blue color of copper sulfate solution has faded. The solution turns light green due to the formation of iron sulfate, or ferrous sulfate. When a strip of zinc metal is placed in copper sulfate solution, then zinc sulfate solution and copper are obtained. CoSO4 plus Zn give rise to ZnSO4 plus Co. In this reaction, zinc displaces copper from copper sulfate compound so that copper is set free, or liberated. The blue color of copper sulfate solution fades due to the formation of zinc sulfate, which is colorless. A red-brown deposit of copper metal is formed on the zinc strip. This displacement reaction takes place because zinc is more reactive than copper. When a strip of lead metal is placed in a solution of copper chloride, then lead chloride solution and copper metal are formed. CuCl2 plus Pb give rise to PbCl2 plus Cu. In this case, lead displaces copper from copper chloride solution. The green color of copper chloride solution fades due to the formation of colorless solution of lead chloride. A red-brown layer of copper metal is deposited on the lead strip. Lead is able to displace copper from copper chloride solution because lead is more reactive than copper. Another point to be noted is that copper chloride used in this reaction is actually copper second chloride. Double displacement reactions. Those reactions in which two compounds react by an exchange of ions to form two new compounds are called double displacement reactions. A double displacement reaction usually occurs in solution and one of the products, being insoluble, precipitates out, separates as a solid. When barium chloride solution is added to sodium sulfate solution, then a white precipitate of barium sulfate is formed along with sodium chloride solution. BaCl2 plus Na2SO4 give rise to BaSO4 plus 2 NaCl. In this displacement reaction, two compounds, barium chloride and sodium sulfate, react to form two new compounds, barium sulfate and sodium chloride. An exchange of ions takes place in this reaction. For example, the barium ions of barium chloride react with sulfate ions of sodium sulfate to form barium sulfate. In this reaction, barium sulfate is formed as a white, insoluble solid, called precipitate, which separates out suddenly from the solution. Any reaction in which an insoluble solid, called precipitate, is formed that separates from the solution is called a precipitation reaction. The reaction between barium chloride solution and sodium sulfate solution to form barium sulfate precipitate, along with sodium chloride solution, is an example of a precipitation reaction. Oxidation and reduction. Oxidation, the addition of oxygen to a substance, is called oxidation. The removal of hydrogen from a substance is also called oxidation. Reduction, the addition of hydrogen to a substance is called reduction. The removal of oxygen from a substance is also called reduction. The process of reduction is just the opposite of oxidation. Moreover, oxidation and reduction occur together. The oxidation and reduction reactions are also called redox reactions. Example: when copper oxide is heated with hydrogen, then copper metal and water are formed. In this reaction, CuO is changing into Cu. That is, oxygen is being removed from copper oxide. Now, by definition, removal of oxygen from a substance is called reduction, so we can say that copper oxide is being reduced to copper. In this reaction, H2 is changing into H2O. That is, oxygen is being added to hydrogen. Now, by definition, addition of oxygen to a substance is called oxidation, so we can say that hydrogen is being oxidized to water. We find that hydrogen is being oxidized to water and at the same time copper oxide is being reduced to copper. This shows that oxidation and reduction occur together. In the above reaction, copper oxide is giving the oxygen required for the oxidation of hydrogen, therefore, copper oxide is the oxidizing agent. Hydrogen is responsible for removing oxygen from copper oxide, therefore, hydrogen is the reducing agent here. Effects of oxidation reactions in everyday life. Oxidation has damaging effect on metals as well as on food. The damaging effect of oxidation on metals is studied as corrosion and that on food is studied as rancidity. Thus, There are two common effects of oxidation reactions which we observe in daily life. These are 1. Corrosion of metals, and 2. Rancidity of food. Corrosion. Corrosion is the process in which metals are eaten up gradually by the action of air, moisture or a chemical, such as an acid, on their surface. Corrosion is caused mainly by the oxidation of metals by the oxygen of air. Rusting of iron metal is the most common form of corrosion. When an iron object is left in damp air for a considerable time, it gets covered with a red-brown flaky substance called rust. This is called rusting of iron. During the corrosion of iron, or rusting of iron metal is oxidized by the oxygen of air in the presence of water, moisture, to form hydrated iron, third oxide called rust. The number of water molecules, kissed smiley in the rust varies, it is not fixed. The rusting of iron is a redox reaction. Rusting involves unwanted oxidation of iron metal which occurs in nature on its own. Rancidity. When the fats and oils present in food materials get oxidized by the oxygen of air, their oxidation products have unpleasant smell and taste. Due to this, the smell and taste of food materials containing fats and oils change and become very unpleasant. The condition produced by aerial oxidation of fats and oils in foods marked by unpleasant smell and taste is called rancidity. Rancidity spoils the food materials prepared in fats and oils which have been kept for a considerable time and makes them unfit for eating. The characteristics of a rancid food are that it gives out unpleasant smell and also has an unpleasant taste. The development of rancidity of food can be prevented or retarded, slowed down, in the following ways. 1. Rancidity can be prevented by adding antioxidants to foods containing fats and oils. 2. Rancidity can be prevented by packaging fat and oil containing foods in nitrogen gas. 3. Rancidity can be retarded by keeping food in a refrigerator. 4. Rancidity can be retarded by storing food in airtight containers.